the opposite direction to dipole moment. That is why we show here a negative sign. Hello, welcome to guidancee education channel. We are continuing class 12 physics, chapter 1, charges and fields. In this video, we will discuss all the formulae that we learned in this chapter. This is by way of revision and this will be very helpful for you. So watch the video completely without skipping. If you think it was useful, like the video, share the video and also leave your comments in the comment box below. If you have not subscribed my channel, do subscribe it now and also press the bell button so that you get intimated as soon as videos are posted. Thank you very much. Come, let us see the video. Electric charge and fields, all formulae in one video. In this chapter, we have learned a number of formulae. We will just recall those formulae so that you understand it better. First one, force due to point charge. 1 by 4 pi epsilon naught q by r square into r cap. I hope you remember all the parameters that are referred to in the equation. Capital Q is the total charge. R cap is the direction. R is the distance of the point from the electric charge. Second one, force between two charges. The two charges are Q1 and Q2. So it becomes 1 by 4 pi epsilon naught Q1 Q2 by R square into R cap. Here R is the distance between Q1 and Q2. Next one, force between multiple charges. Q1 by 4 pi epsilon naught sigma Qi by R1I raised to 2 R1I cap. Limit of I is equal to from 2 to n. We assume that there are n number of charges. Okay. Electric field 1 by 4 pi epsilon naught Q by R square into R cap. This equation looks more or less similar to the first equation, but there is a difference. What is that difference? In the first equation, capital Q is the total charge. In the case of electric field, it is due to unit charge. So we have used here small q in order to identify that. So electric field is force due to unit charge. That is the only difference. Now we will see electric field due to multiple charge. Q1 4 pi epsilon naught sigma Qi by R1I raised to 2 into R1I cap, and the limit of I is equal to 2 to n. Here also we assume there are n number of charges. I hope it is clear. From the expression for electric field, we can get expression for force. What is that? This equation 1 by 4 pi epsilon naught q by r square into r cap. This equation is for unit charge. What is force? Force is for the total charge. If the total charge is capital Q, then all you need to do is force is equal to Q into E. That is total charge into electric field due to unit charge, or it may also be written as QE instead of capital Q. Sometimes small q also may be used, but you should understand whether it is capital Q or small q, it is the total Q or total charge that is considered. So from this expression you get the expression for electric field. E is equal to F by Q. That is force by total charge. Then you get force for unit charge. Force for unit charge is electric field. I hope it is clear. Now we will pass on to the next set of equations. Let us continue. Seventh one, electric flux. Symbol is phi. Delta phi is equal to E dot ds. Total flux is equal to sigma, that is total, E dot ds. Limit is from 1 to n. We consider there are n area elements. Okay. E dot ds is equal to E ds cos theta. It is dot product. Now, electric dipole moment P is equal to 2qa. Actually, the formula is q2a. We rearrange it and write it as 2qa. Now, field due to electric dipole at a point on the axial line 2p by 4 pi epsilon naught r raised to 3 in the direction of dipole moment. Okay. Field due to electric dipole at a point on the equatorial line p by 4 pi epsilon naught r raised to 3. It is in the opposite direction to dipole moment. That is why we show here a negative sign. If the dipole moment direction is along this direction, here electric field direction also is in the same direction. But in this case, electric field direction is in this opposite direction. That is why a negative sign is used here. Okay. Torque on dipole in uniform electric field. The dipole may rest at an angle to electric field or parallel to the electric field or anti-parallel to the electric field. The torque has direction and magnitude. It is a vector. Torque is equal to 2qa e sin theta. 2qa is dipole moment. So Pe sin theta. Direction depends upon the direction of orientation of the dipole and also electric field, and the direction of the torque will be normal to the plane of paper. Dipole experiences translatory motion. When it is parallel to the electric field or anti-parallel to the electric field, the formula is the same. When it is parallel to the electric field, there is no torque. It is called stable equilibrium. And when it is anti-parallel, it is unstable equilibrium. The dipole aligns with the direction of the electric field. So that is a motion of the dipole. Torque direction is different. Next is torque on dipole in non-uniform electric field. It experiences translatory and rotational motion. The force at the two ends of the dipole will be unequal. So it experiences translatory and rotational motion. Electric field due to continuous charge distribution. Field due to line charge distribution. This is different from discrete charges. Delta E is equal to 1 by 4 pi epsilon naught lambda dl by r square into r cap. This lambda is linear charge density. Similarly, surface charge distribution delta E is equal to 1 by 4 pi epsilon naught sigma ds by r square into r cap. That gives the direction. This sigma is surface charge density. ds is a small area element. Similarly, dl is a small length. Now, volume charge distribution, which is otherwise called charge distribution. Delta E is equal to 1 by 4 pi epsilon naught rho dV by r square into r cap. This rho is volume charge density. dV is a small volume. For the three cases above, for the whole length, whole surface and also whole volume, we have to integrate delta electric field for each segment. Now let us pass on to Gauss law. Gauss law, flux is equal to Q by epsilon naught. This is for a closed surface enclosing charge. Electric field due to infinitely long wire. Applying Gauss law. Formula is E is equal to lambda 2 pi epsilon naught r n cap. This gives the direction. Electric field due to large plane sheet where we consider parallelepiped cross-sectional area or a cylindrical cross-sectional area. E is equal to sigma by 2 epsilon naught n cap. The sigma is surface charge density. Electric field due to a uniformly charged spherical shell at a point outside. E is equal to Q by 4 pi epsilon naught r square. Inside the shell, it is 0. On the surface, It is E is equal to Q by 4 pi epsilon naught capital R square. For electric field outside, at a point outside, the small r is greater than capital R. On the surface, small r is equal to capital R. So, on the surface, it is maximum. This video will be of great use to you. This is a ready reckoner. If you remember all these points, you will not miss any question from this chapter. It is guaranteed. Moreover, I have given each of these formula in separate videos. You can refer those videos also and then clear your doubts if at all you develop any doubt. Okay. We will meet in the next video with another important chapter. Okay. Thank you.